Hi everybody, thank you for coming. I'm Alan Perry and this is Tianqi Wang. We're going to be going over our projects at UCSF in the last year. We've been a part of a team of data scientists and medical researchers that have come together to answer the question, how can modern deep learning be used to answer modern medical questions? We're going to first go over our published work and then the work that's currently under review and then that which we're currently working on and will hopefully be published soon or submitted soon. Our first problem and project was on organ segmentation. This is if we're given an image, how do we answer where is an object in that image? So a set might look like this, where we're given an image and for each location in this image, we answer the question, what is at this location, and is there anything at this location at all? Our data for this project was 125 three-dimensional CT scans. And we also had corresponding labels that were handmade by medical professionals. This is our model, and I won't get too much into the technical details, but our novel contribution was that we added attention-gated skip connections, which allows our model to learn what part of the anatomy should be paid attention to whenever it's making a prediction. This has been shown to increase performance in multiple fields, but we wanted to see if it would have similar results in the medical realm. And here's the results of our model. You can see at the top a manually made label, and at the bottom predictions outputted by our model. I think you'll agree that the results visually look very similar. But if the visuals don't persuade you, we also have a similarity metric that's known as the DICE score. It measures the overlap between our predictions and the actual labels. And we used this score to compare our model with other models. And ours came out on top. For our next presentation, for our next project, we were inspired by a model which takes two sets of unpaired images and uses a similar structure between the two sets to translate between them. We had a similar problem in the medical realm that we would like to take MRIs and translate them to CT images. This is a very similar problem because you'll never have an MRI and CT at the exact same location. I again won't get too into the weeds about our model, but the change that we made was that we added a variational autoencoder to discriminator, which allowed our model to have a larger space that it's choosing its real values from. And that allows for better translations. And here we've again given outputs of different models as well as an output of our model and the actual. I think you'll agree that ours is visually more similar to the actual image that we're trying to predict. And at the bottom we have statistics, which I think show that our model is, again, closer to the actual. And now I'm going to pass it off to Tianqi, who's going to talk about current work.
Our current research consists of two projects. First one is 3D dose volume diagnosis. So the conventional radiotherapy treatment planning process consists of an iterative back and forth procedures between a treatment planner as well as an oncologist. So this procedure could take few days to make a treatment plan to complete it. So we think an automated treatment planning system has a potential to reduce the work for both treatment planner as well as oncologist. So we develop a planning model which is called dose-scan, which is based on a conditional adversarial, generative adversarial network architecture, which can automatically generate those created dose volume diagnosis based on CT images as well as label of different organs. So you can see from this picture, our model has a really good predictions, which is really close to the clinic plans. We almost finished this work, and the paper should be submitted soon. And the second project we are working now is adversarial defense. So we know that deep learning models has been widely implemented in various industries, but the model itself, to most of people, is more like a black box. Sometimes how the model will understand data could be quite different with how human will understand the data. And this could make the model quite vulnerable and easy to be manipulated. For instance, in this case, a model is trained to predict the species given the picture. Well, at first, it correctly predicted the species to be panda, but after adding some word noises, the model has generated totally different predictions, while people can barely tell the difference of these two images. And the process that generated those noises is called an adversarial attack, while the strategies implemented to make the model more robust to this kind of attack is adversarial defense. The adversarial attack could be a huge problem for the deep learning models implementation in medical areas, which is super sensitive to the accuracies. So we try to solve this problem. Firstly, we build a really good model to make segmentations based on CT images. The segmentations is for 3 different organs. You can see from this picture, the model is well trained to make those predictions quite close to the ground truth. But on top of this, we build a text systems to generate some noises to mess up this model. You can see after adding those noises, the model's prediction has been quite messy, and these two input images, people can barely tell the difference. We almost finished the building work of the attack systems, and now we're trying to implement different strategies to defend this kind of attack. This is the paper we submitted, and the first paper just published this morning, and the second paper hopefully should be published soon. And for all technical details, you can refer to these 2 papers. And also, if you're interested in our current research, you're welcome to talk to us afterwards. This is our presentation. Thank you. We will also thank Vasan and Brian for the technical support. We will also thank Wicklow for the funding support. Thank you.